Hello, we're working on Chapter 2, Section 6, all about related rates. And you may be asking yourself, what would that topic look like? Well, let's switch over. I'm going to switch into Geometry Sketchpad here, and we're going to watch this balloon get inflated. And it talks about a spherical balloon is inflated at a rate of 10 cubic centimeters per second. How fast is the radius changing when the diameter is 1 centimeter, 2 centimeters, or 4 centimeters. So we'll just hit inflate. Notice the balloon getting larger and larger and larger. As this is happening, several variables are changing. One thing that's changing, the balloon is getting larger, meaning the volume is increasing. Not only is the volume increasing, but you could really tie the volume to the radius of the balloon is changing. The radius starts small and then gets larger and larger, which would mean, of course, the diameter is getting larger too, which also means that the circumference gets getting larger. As this volume gets larger, so does the surface area. So there's a lot of rates here that are related, and that's where we come up with this topic of related rates. I'm going to let's show the volume here. There's a volume curve, and it's the rate stays steady, and that's why we get a linear function out of that, because it's constantly coming in at 10 cubic centimeters per second. Let's show radius. Well, initially, when we start this balloon, watch, it starts very small, and then it's going to get large quite quickly. So fast in the beginning that it's hard to follow. Here's the curve for the radius. As that balloon picks up volume, the radius is changing less quickly as we move to the right in time. We could show the volume, dv dt, which is the change of volume over change of time. And notice that we get a linear function up there. It's nice and steady. And dr dt, we can also show that. And look at that red line. Initially, that radius changed a lot. It went from a very high point, and very quickly the radius, the rate of change of radius is slowing down, and we come down into this lower y value. So I think that's kind of a cool depiction of what's going on when a balloon gets inflated. And this leads us into the related rates application. So what I'm going to have you do first is let's just talk about the process of solving related rates problems. One, a diagram can be very helpful, and I'd also label your variables. Next up, the rates. In the problem, we're going to be told how fast something is changing. So on that balloon, they told us they were putting 10 cubic centimeters of air per second into the balloon. We're going to write down those rates. Next, we'll try to write some equations. We want to write an equation, and this part's important, that ties the variables together. So like in the balloon, let's just pretend it was a perfect sphere. So I know the volume equation is 4/3 pi r cubed for a sphere. What's getting tied together here is the volume with the radius. And that's what we mean by we're able to write an equation that ties together multiple variables. Often these equations will be geometric. Example, the sphere, a cone, a cube. We also could do things that involve the Pythagorean theorem, so don't forget that powerful theorem on these problems. Another thing that you're going to do after we get our equations written, or an equation written, we will take the derivative, which will be implicit differentiation. We're going to take both sides and differentiate with respect to t most of the time. For our problems, I think it probably always will be t, which is with respect to time. And this forms our related rates. Finally, the last thing we'll do is substitute and solve. We'll substitute some of these values that we wrote down back here in the second step into our derivative equation. So we talked about inflating a balloon, and our spherical balloon is inflated at a rate of 10 cubic centimeters per second. How fast was it changing? How fast was the radius changing when the diameter was 1 second and 1 centimeter and 4 centimeters? Okay, so let's just kind of follow our pattern. We said let's make a diagram. Well, we've got a sphere, so do your best sphere that you can. And here's the center of my sphere. Important things about a sphere, mainly it's all driven by the radius, isn't it? And the next thing I'm going to do is take note of the rates that they talked about. A spherical balloon is inflated at 10 cubic centimeters per second. We'll just look at the label on this and you can tell it's a rate. Cubic centimeters talks about volume. So my volume is changing at a rate. And I'm going to note that by saying dV, the differential of the volume, compared to the differential of time, change of volume over change of time, was 10 cubic centimeters per second. How fast is the radius changing when the diameter is 1 centimeter and 4? Let's just immediately take this down to 1/2 and 2 centimeters. So we were talking about radius. Well, there's a couple things they want to know. They want to know how fast the radius is changing. This fast is going to be a rate, isn't it? This is going to be noted in a rate. So here are things that we know, and now here's the thing that we are seeking. We seek to know the change of radius over the change of time. Would love to know that. And we're going to take a snapshot of this. So here's my little camera. I'm going to take a snapshot, press the button down. I want to know what's happening when radius is 1/2 centimeter. So at the precise moment when my radius hits 1/2 centimeter, what is the rate of change? And then also it looks like we're going to look at it when the rate is 2 centimeters. Well, the one equation that's going to tie together radius with volume would be the geometric equation for volume of a sphere. And so there are things that you are going to have to memorize. This would be one of them, and most of you probably already know this. 4/3 pi r cubed is our formula for volume of a sphere. Now what we're going to do is we wrote down our rates, we wrote down the equation that ties it together. The next step is looking at this. We wrote the equations. Let's go into taking the derivative. To do that, we need to implicit differentiation on this. So I'm going to have dv dt. We're going to take it with respect to time. 4/3 is just a multiplier as well as pi, because pi is just a number. Now what we need to do is take the derivative of r with respect to time. The 3 comes down, the radius goes to r squared, and then it would be dr dt. Now, what did they ask us to find? They wanted us to find dr dt. My dr dt is sitting over here, isn't it? Well, I can plug in my variables or my knowns and then solve for that. So dv dt was given to us in the very beginning as 10 cubic centimeters per second. So I'm going to put 10 in there. Notice over here the 3's canceled, so let's let those go. And we get 4 pi, and r is a known quantity at this precise moment at 1/2 a centimeter for radius. We want to know what dr dt is. Well, if I do a little bit of work, now we're just down into solving the final step. 1/2 of 4 is 2. We get 2 pi dr dt. And let's solve for dr dt by dividing by 2 pi. And we will get an answer of 5 pi equals dr dt. Labeling is important, and I didn't track my labels up in the thing, but I know that radius was in centimeters and time was in seconds. So I'd have 5 pi centimeters per second. So what, approximately 15.5-ish, 15.5 centimeters per second. You can go ahead and do 2. I'm going to move on so I can save time on this. Ripples on a pond. A pebble is dropped into a calm pond. Ripples radiate forming concentric circles, kind of like this diagram. Remember a concentric circle? They are circles that share the same center. The radius of the outer circle is increasing at a rate of 2 feet per second. When the radius is 5 feet, at what rate is the total area changing? So a few key words in here. Area, the radius of the outer circle is increasing at a rate of. And what else did they? The radius is changing at 2 feet per second. So that's a given right there. And then when, this is at the precise moment, a snapshot idea. Let's talk about a diagram, not, super important, it's just a circle. And we have a radius here. And then they talked about the area of this circle, correct? So the next thing I want to do is let's just jot down what they gave us for rates. They said the radius is changing at a rate. Well, anytime I see the word rate, I think of the derivative. So the derivative of radius dr dt is 2 feet per second. When the radius is at 5 feet, what is the rate of the area changing? dA dt is equal to something when, this is the snapshot, when r equals 5. And I have to wait till I get my differential equation written before I can throw in the 5. So this was our known value, and this is what we are seeking. The equation that's going to tie together area with radius of a circle is area equals pi r squared, correct? Area of a circle, another one that we just know or have memorized. Now I need to get to dA dt. Well, that's simple. Just take this equation and let's do the derivative on it. dA dt would be the derivative of a equals pi, which is a multiplier. The derivative of r squared would be 2r dr dt. We can clean it up a little bit, not a lot of rearranging here. dA dt is equal to 2 pi r. Oh my gosh, that's circumference, isn't it? 2 pi r dr dt. Now, let's go back to what we knew and plug in our known values. We had dr dt at 2 feet per second. So I'm going to have 2 pi r times 2 feet per second. You know what, I'll put the label in there, feet per second. And radius, we also, so we want to find dA dt. We know at the precise moment when it's 5. So dA dt is equal to 2 pi, throw in the 5. That would have a label of feet. And then we've got this 2 feet per second. Notice how we're getting a rate out of this. dA dt, all we have to do is multiply on this one to solve it. 4 times 5 is 20 pi. Feet times feet give me feet squared per second. And that label looks perfect for area. Feet squared changing per second. Finally, the last one is all about a cone. Water is flowing into a cone at a rate of 2 cubic centimeters per minute. How fast is the water level rising? At 10 centimeters and 15 centimeters. I've also got a quick video on this one. We could watch the water filling in this cone. So here we go. Notice how the radius is changing the more volume we pick up. Also changing is the height. So we've got like 3 variables changing here, very easily to see. The height is changing, the radius is changing, the volume's changing. You could even look at the area of the top surface of this cone changes as it fills up. So many things going on. We got an idea about that. Okay, let's go back over to our problem. Water's flowing into a cone at a rate of 2 cubic centimeters per minute. How fast is the water level rising? So I want to talk about a diagram. Okay, draw yourself a cone, put in a height, put in a radius, and we've got a certain amount probably of water in there right now, right? So here's kind of that surface area on top of this. Well, what else do I know? Let's go in, we did our diagram. Let's talk about rates given. Water's flowing into it. Notice this label. That's a key indicator that we're talking about volume. And it is per minute, so this is a rate. dV dt is equal to 2 cubic centimeters per minute. How fast is the water level rising? Well, they want to know how fast the water level is rising. What is the height changing? The rate of height changing. When, I always like to write the word when because it just gives me an idea of this is the snapshot period. When I stop the clock at 10 centimeters or at a certain time, I'm going to stop it when the radius hits 10 centimeters, and then I want to know this rate of change that occurred at that precise moment. It's kind of, you can make the analogy to that instantaneous velocity that we've done before. At this precise time, what was the velocity? Well, now at this precise time, what's the change in height? What ties together R, V, and H? Well, the geometric formula, volume equals 1/3 pi r squared H, the volume of a cone. Let's take the derivative of each side. Ooh, if I take the derivative of each side, it's going to get a little interesting right here with the R and the H, because that would go into product rule. So what we may want to do is change up this R in terms of H. How could I do that? That is a good question. I'm going to continue this video on the next screen or in a new video because we're hitting the time limit. See you back in a minute.